Hello. In this video, I will be taking a look at multiprocessing versus threading in Python. Now I hear these two statements quite a lot with regards to multi-threading in Python. The first one being that Python is multi-threaded, and the second statement being that Python is not multi-threaded. So which one's right? Well, I think the correct statement is actually that Python is multi-threaded, but is not simultaneously multi-threaded. That is to say, two threads cannot execute simultaneously. So what is a thread? Well, to understand that first, we need to ask what a process is. A process is an instance of a program. This may be an instance of Firefox, or several instances of Microsoft Word, for example. A process has memory set aside for its code and its data. A process then has at least one thread, which has its own registers and stack. This thread has access to the data of the process. The thread is the smallest sequence of instructions that can be managed by the OS. That is to say, the OS determines when and for how long the thread can run. A process can spawn another thread, or be multi-threaded, with each thread having its own register and stack. That is to say, its own space in memory, but most importantly, it has access to the process memory space. Thus, a thread can access the data held within the process. Even if the Python implementation creates user-level threads instead of kernel threads, the user, using the thread package, will be able to access the data from the process. If another instance of the same program is launched, it does so with its own code and data space in the memory. These processes can all have their own threads. Most importantly, however, is that the data is not accessible between processes. The data space from one process is not accessible to another process. In order for the two processes to share data, they must do so via queues or pipes. Likewise, threads can also utilize queues and pipes to share data, but pipes and queues have some overhead to consider. So having a look at threads and processes in a bit more detail in Python. So here, as an example, we have two processes, process 0 and process 1. Each process will have two threads, thread 0 and thread 1. If we consider what happens on a 4-core CPU, we see that threads in Python are concurrent but not parallel. That is to say, each thread is subdivided in time, and a little bit of progress is made for each thread, but no two threads from the same process are ever executing at the same time. Both threads and processes can jump around on the physical CPU cores. This behaviour can be suppressed by asking the OS for an affinity to a certain CPU core, but that is up to the OS as to whether to do so. In any case, each thread of a given process cannot execute simultaneously. That is the most important thing to remember here. That in Python, no two threads from the same process can operate simultaneously. Processes, on the other hand, can execute simultaneously. As you see, threads 0 and thread 1 from both of the individual processes can run simultaneously because they belong to individual processes. In order for a thread to run, it must acquire a protected global interpreter lock within the process. By ensuring only a single thread can execute at any one time, thread safety is guaranteed in Python. And by thread safety, we mean that there can be no deadlocks. This actually does improve single-threaded performance, but it prevents simultaneous multi-threading within a process. That is to reiterate, two threads cannot execute simultaneously, meaning intense CPU tasks cannot be parallelized. But on the bright side, I/O limited threads are hardly affected at all, since they spend most of their time waiting for data to come in or waiting for a return signal for data going out. And so if you go back to our previous example, and instead of looking at CPU bound task, we look at I/O bound task, where here thread 0 in each process is an I/O bound task, we can see that here, thread 0 in both processes has some I/O operations. These I/O operations are blocking, that is to say, once the I/O request is made, the thread must wait for the return value. So this could be, for example, reading or writing to a file, reading or writing from a serial port, or fetching a URL. In Python, once an I/O request is encountered, the interpreter releases the global interpreter lock, allowing other threads time to execute. If thread 1 is a CPU limited task doing lots of things, then being interrupted occasionally to do some I/O is acceptable. especially if the alternative would be to do some long processing operation, then request and have to wait for the data to come in before continuing. With Python threading, the work can be done while the next lot of work is being requested. And so now we can go ahead and compare threads and processes in Python using a few different metrics. So for the setup cost in terms of both time and resources, threads are less costly than processes. For the handling, the CPython interpreter handles the threads, where the OS handles the processes. For memory access, threads have access to all the data of the host process and can use this data space to share with other threads, whereas processes have separate data spaces. For execution, both are concurrent, but importantly in Python, threads are not parallel. Two threads cannot execute simultaneously in time. Processes can. This is sometimes hard to explain, so let's look at an example. So here we have a function that takes in a timestamp, t0, and an array. The array is set up so that it has chunks of time in 50,000 nanosecond intervals, that is 50 microsecond intervals, in the first column, and 0 for the second column. The function enters an infinite loop where it simply evaluates the time since the timestamp using the performance counter. It adds 1 to the row in which the performance counter is binned into. For example, if the performance counter returned 75,000 nanoseconds, then the second row of the second column is incremented. Once the time exceeds the maximum time in the array, the function returns. In the end, the array will be populated as a histogram with the number of times the loop was executed within the 50 microsecond time increment, and as you can see, this is an intensive function that is always doing something, and importantly, none of the operations are multi-threaded behind the scenes, so it is indeed single core limited. We can then go ahead and import the threading library, and we can create a number of threads, and we can give them all a deep copy of this array, and then we run each thread, and the deep copies of the array will then be populated with the data from this function f. So what does that look like? So here are the results for 4 threads. I should say here that the CPU I'm running is an 8-core CPU with simultaneous multithreading enabled, hence up to 16 kernel threads can execute simultaneously. We're only using 4. The horizontal bars on the left indicate if the histogram was populated for that particular time interval. So this is an activity plot for the threads. Whenever there's colour, it means the thread was doing some work. We can see that at any one point, only one thread is executing. The threads are all in discrete chunks of 15 milliseconds, which is no coincidence. CPython will allow a thread to run up to a blocking IO call, or 15 milliseconds, whichever happens sooner, before another thread is given a chance to execute. Very rarely a thread will be reassigned to run after it's forced to stop after 50 milliseconds, which results in a small pause. Over the 3 seconds to which this activity plot was generated, this represents 200 lots of thread allocation chunks. The amount of time each thread has executed for is plotted on the right. You can see that the threads are not evenly executed despite all doing the same thing. Overall, only around 3 seconds of work has been done across all the threads, and the total number of function calls across all the threads was around 2 million. When switching to 8 threads, the situation is very similar, but we see a lot more asymmetry in the time that the threads have been allocated during this 3-second window. You see a few dips in some of the chunks. This is where the OS jumped in and paused the thread briefly in order to do something, such as move the thread to another physical or virtual processor. This results in at least a 50 microsecond window where the no function iterations were completed. And again, despite having 8 threads, they collectively only do about 3 seconds of work in total, spread across these 8 threads. And we see a very large asymmetry, where some of the threads are really not getting a lot of execution time during this 3-second window. In particular, threads 2 and 7 look like they've been given the wrong end of the stick, not actually performing a lot of work, as compared to, say, threads 0 and 1. The total number of function calls this time, across all threads, was again around 2 million. So around the same number of actual function calls were performed, despite doubling the number of threads allocated. When using 16 threads instead, we see a very large amount of asymmetry for the first 3-second test again. And again, what we'll see is that overall, only around 3 seconds of work will be done across all 16 threads, with a large degree of asymmetry now, across all of the threads. You can see that the threads with a lower index tend to be getting a lot more of this initial chunk of time than any of the threads with a higher index. In fact, as you can see currently, none of threads 12, 13, 14 and 15 have actually had any time allocated to execute. And so the total number of function calls for these 16 threads again was around 2 million. So even doubling further from the 8 million, there has still been no improvement as to the actual work done by the threads. And so how can we actually improve this? If we had this CPU limited task, how would we go about actually increasing our performance using our multi-core systems? So we can go ahead and look at using multiprocessing, which is a standard Python library used to do what most people think of when they actually say multi-threading, by using multiprocessing to process several processes simultaneously. So if we can take our code and we can make a few changes. The first thing we must change, in particular for users on Windows, is to change the offset time to time.time. This is because the performance counter is relative to the start time of the process. Since we are spawning multiple processes at different times, we cannot use the perf counter for the offset. We also can't use the time.clock, as this has been depreciated and will be removed in Python 3.8. Time.process time is also out, as this is process specific. Luckily, the time.time function on at least my machine has a resolution of around 1 millisecond and is not process specific in reference, and the 1 millisecond is an acceptable offset. So we're using time.time for synchronization to synchronize to around 1 millisecond, and time.perf counter for high performance binning. Also, we must make sure that we return the array this time. Because processes don't share memory, we are sending a separate copy of the array to the process, which then it must send back. So what we do is we go ahead and create a number of deep copies of this array, and then we create a pool of workers using the multiprocessing pool class, which will automatically send our array using the star map function, and then also handle the return array back to us in order of the out sending. We make sure we send a reliable timestamp, which is our T0, to the individual processes for the synchronization. There is a lot of overhead associated with processes, including the communication. I do have another video on my channel where I look into this, but for this video we are only interested in how the execution is happening. So we'll only be looking at the performance of the processes. So if we look at the activity plot again, but this time with our 4 processes, we can see now something very different. We can see clearly that each process is executing simultaneously. So each process has activity happening at the same time as the others. Also, because they are running in parallel, their processing times are near identical. All 4 processes start at roughly the same time, thanks to the fact that we're sending a relatively small array to each process, and the process does a lot of work on this array. We are actually doing around 4 times the work than we could have done with multi-threading, so this is actually speeding up our performance. In fact, over the course of this 3 seconds, we actually perform 9 million function iterations, which is more than 4 times as many as the threading interface provided at around 2 million. You do get the occasional hiccup where the OS did something like switch a process to another core, etc. But overall, it's a massive improvement over a single threaded application. When moving to 8 processes, we start to see something very interesting. Each process has a different start time that exceeds the accuracy of the timestamp, meaning they do indeed start at different times, and this is because we still only have a single process, the main process, with a few threads handling packing and sending of the data to each worker process. And as we know, these threads can only execute in non-parallel fashion, so multiprocessing is better suited for very intense CPU-limited tasks where each process has to do a lot of work without spending an appreciable amount of its time on input and output. We see that since my CPU has 8 cores with simultaneous multithreading, I can use 8 of these cores with almost full utilization, and Windows still has enough processing cores to do its stuff behind the scenes. We do occasionally see a hiccup where some background process required a lot of multi-core CPU power, and so competed with these Python processes for CPU time. But in general, we are actually doing around 8 times as much work as we could have done with multi-threading. Overall, 16.7 million function iterations were made, which is around 85% more than for 4 processes, but 8 times more than using the 8 threads. So the improvement is still appreciable. If we then go on to our 16 processes example again, but this time using multiprocessing, things get very interesting. Remember, my CPU is 8 physical cores with simultaneous multithreading enabled, giving 16 simultaneous compute units. Here we can see that the start times of the processes are all quite spread. This spread is over about 180 milliseconds, which dwarfs the previous 10 milliseconds for the 8 threads. We see now during these 3 seconds we have some processes that run relatively uninterrupted, but processes like 9, 10, 13 and 14 are being constantly interrupted, resulting in lower progress overall, despite getting a head start. This is not surprising, as the OS has to manage all these processes, and occasionally something more important comes along that the OS must deal with, and its scheduling algorithm will decide to kick off some of our threads in order to do something else. But in general, we are still doing around 14 times as much work as we could have done with the multi-threading, so it's still a massive improvement. And the total number of function calls made here was around 20.6 million, which is only 23% more than for 8 processes, despite doubling the amount of processes, which is quite strange. Or is it? Because the actual SMT technology, so even though it's 8 physical cores and 16 simultaneous cores thanks to simultaneous multithreading technology, you don't actually get double the performance. The typical performance increase is around 25%, which is what we're seeing here. And so just comparing the activity plot for both packages, we can see more clearly that the multiprocessing is doing more in the same amount of time than the threading. And so, if we look at the actual work done by both multithreading and multiprocessing instead of just the activity plots, we see that adding more threads did not result in any more work being done during those 3 seconds, whereas multiprocessing achieved excellent scaling up to 8 simultaneous processes, which is the same as the physical number of CPU cores, and then also another extra 25% from utilising simultaneous multithreading technology for the next 8 cores. And all while bearing in mind that the operating system still needs some CPU time to do things. And so what have we learned? If we take a look at the 2 different types of tasks that threading and multiprocessing really cater to. If the task is CPU limited, and by that we mean a large amount of CPU work is required, like the examples we saw in this video, multiprocessing is the way to go. If the task is I/O limited, such as waiting for serial data to come in, waiting for URLs to resolve, etc., multi-threading is the way to go. The program can do other things while waiting for the I/O, such as refreshing a GUI or processing the previous chunk of data. In fact, threading is excellent for GUIs or interactive figures. You can check the GUI input 60 times a second, for example, which requires very little CPU time, and so it makes the GPU very responsive because you're checking whether or not the user has interacted with the GUI many times a second. But the actual processing power associated with that is a very small chunk of the actual total processing power available for that single thread. And so any background tasks, such as actually changing the GUI or doing any data operations in the background, are basically just as fast. And a word of warning, incorrectly using either one of these multiprocessing or threading libraries can actually cause your program to run slower, as both of them are associated with some overhead. They're not for free. And also be careful with some types of CPU limited tasks. The back end of modules like NumPy and SciPy are heavily optimized and utilize simultaneous multithreading in the native C code they are written in. These functions will not benefit from multiprocessing if they use all available cores. And just touching on this idea that the multiprocessing can actually be slower a bit more, in a previous video I showed how multiprocessing may not offer a speed increase due to the large overhead associated with packing, sending and receiving tasks to and from each worker in a process. It is entirely possible to get a massive performance hit when using multiprocessing incorrectly. This can often occur when you have a simple function that doesn't actually do a lot and you're sending a lot of data to that simple function. the overhead associated with sending that data to the process dwarfs the saving in computational time from having that done simultaneously. The ones that benefit the most are the ones where a lot of operations must be performed on a relatively small amount of data. And so in summary, what have we seen? We've seen that Python is most certainly multi-threaded. It's concurrent, not parallel, and that the CPython implementation will consider switching threads every 15 milliseconds or so, or when an I/O operation is encountered. Threads are a great way to divide up work in a discrete time fashion, and is very useful for things like GUIs where you only have to check occasionally for some interaction, or for programs where there is a lot of time spent waiting for data to come in, or waiting for these I/O operations. Multi-threading does not strictly mean single core. The OS may switch the Python process between physical and virtual CPU cores. In a lot of sense, you're up to the mercy of what the OS decides to do. And multiprocessing is the standard Python way to increase processing power if needed. It's part of the standard Python library. And most numerical libraries such as NumPy, SciPy, TensorFlow, etc. are simultaneously multithreaded behind the scenes, so you won't necessarily get any speed increase when using multiprocessing. And here are some of the things I did not go through in this video, but that you should watch out for. Since threading allows process data to be accessed, data may need to be protected with a lock. So locks ensure that if a thread is interrupted halfway through changing or accessing some data, another thread cannot modify it during that interruption. E.g., if some data was updated by several write operations, reading an intermediate value could return nonsense. Locks can be used to protect these operations. If you're using a pipe to share data, they may become corrupted if accessed simultaneously. Pipes are not thread safe. Queue, on the other hand, can be accessed simultaneously and by multiple users and by multiple processes. That is to say, queue is thread and process safe. However, queues are more costly than a pipe to set up, so use the one most appropriate for your application. And so thank you for watching. I hope you found this video informative, and stay tuned for more content like this.